Welcome everyone, and thank you all for joining us. Today we are talking about distributed galvanic anode design. This is a how-to design tutorial focused on using distributed galvanic anodes for galvanic encasements, marine pile jackets, and including bulk anode selection. This is the second of a three-part series showing you how cathodic protection systems are designed. And before you ask, yes, today's recording and slides from the presentation will be made available on our website. So if you missed anything, we've got you covered. This year also marks the 25-year anniversary of Vector Corrosion's GalvaShield product lines. Over the past quarter century, we've been at the forefront of providing innovative and effective solutions to corrosion-related challenges. Our mission with the webinar series is to do our best to pass along some of the lessons we've learned along the way and help you harness the best practices for concrete preservation and sustainability. I also want to take this opportunity to invite you to next month's presentation on designing with two-stage anodes. Please note that the date has been moved from June 19th to June 26th. So if you've already registered, make sure to update your calendar. The series is also brought to you by some of Vector's partners you see on screen. We'd like to thank Cosepi, Credence, eStop, Hakron, Rahid, Sika UK, Poplar, Tradewinds, and Whale Built for their support and participation in bringing these educational sessions to you fine people. A challenge to you all before we start, we ask that you provide us your name when you ask questions in the chat function. This is because we are giving away a $100 Amazon gift card to the best question, which will be picked by your presenter. So you can ask as many as you want, so please ask away. And one final call out. Before I introduce today's speaker, we put together this environmental impact calculator, which is a free tool to use on our website, just under the resources tab. And what it does, it allows you, with a few simple inputs, generate a statement of all the energy and resources your efforts have or will conserve when you preserve a structure instead of replacing it. PDF is easily shared and to help you show the difference you make with your decisions to save structures. And here he is. Shayan Yazdani is a project engineer hailing from VCS Engineering. He is a civil engineer specialized in corrosion assessments and cathodic protection designs. He lends his expertise of the AMPS Standard Committee as well as serves as the secretary for ICRI's Corrosion Committee. Suffice it to say, he's very qualified to present on today's topic, and so with that said, I'm going to let him get started. Shayan, take it away.
Thank you, Ben, for the introductions, and good morning or good evening to everybody that's joined us on this series today. Thank you for your time. And as Ben mentioned, I'll be talking about the design of distributed galvanic anode systems today. And with that, I'm going to go a little bit into the corrosion background, touch base on what corrosion is, how it occurs, and how can we tackle corrosion, and then cover some of the different types of distributed anode systems that are out there today for various different applications. Some design parameters that are important for designers and engineers and even owners to know about before digging deep into designing the system itself. And then covering some marine pile jacket examples and galvanic encasement project examples. So with that, going into the corrosion background, we know that corrosion is an electrochemical reaction. It has an electrical circuit component and it has a chemistry component to it. And it requires 4 main components in order for the corrosion cell to occur. We need to have an anode. That's where, that's the section where we lose an electron and that electron is transferred to the cathode. And at the anode site, as that electron is lost, we tend to have rust formation and cross-section loss. And as the cathode receives that electron, obviously the cathode is protected. There's no section loss there. Both the anode and the cathode need to be submerged in some sort of an electrolyte. In my practice, that would be concrete. I specialize in reinforced concrete structures. But again, it doesn't always have to be concrete. In pipeline industries, that can be soil. In marine environments, that can be water. And the last component would be the metallic path. So we need a metallic path that connects the anode and the cathode together so that the electron can get transferred. And again, in my world, that would be the rebar itself. So the rebar is the anode, the cathode, and the electronic path, and the concrete would be the electrolyte. And again, the big takeaway from this slide is really to understand that it's at the anode site where we have rust formation and section loss, and not at the cathode. And so what happens when we have corrosion activity? Obviously, iron particles want to go back to their original state, which is an iron oxide. And so here, on the right, we have a graph where it shows an iron particle's relative size of 1. And as it reverts back to its original state and it becomes an iron oxide, it's extremely expansive. And we can see the relative size of that iron oxide is almost 6.5, 7 times a regular iron particle. And so because of these expansive properties, it puts a lot of stresses onto concrete. And we know as engineers that concrete doesn't really perform well under tensile stresses. And so in order to relieve that stress, the concrete tends to crack, delaminations are formed, and then that eventually over time leads to spalling. And that's where we see deterioration of our infrastructure. And so what can we do to tackle corrosion? And what is cathodic protection? That's one of the methods that we can use. And cathodic protection is really the application of using direct current to make our intended structure that we want to protect and force it to become a cathode. And typically we can do this by 2 different types of cathodic protection system. One is a galvanic CP system, one is an impressed current cathodic protection system. And in today's presentation, I'll be focusing on the galvanic CP system. And so on the image here, we can see we're using a galvanic anode. Going back to the first couple slides where I showed the corrosion reaction, it's very similar. So we're using a galvanic anode, and we're connecting that anode with an electronic path. In our case, that would normally be a wire or just a direct connect to the steel or structure that we're trying to protect. And so that galvanic anode sacrificially corrodes itself, passes the electrons to our steel that we want to protect, and essentially protects the steel from further corrosion activity. Going into the distributed anode systems, they're extremely versatile anodes. They can be, we've used them on a number of various different projects, such as bridges, piers, cathodic protection jackets, overbuilds, expansion joint repairs, and road widening or deck widening projects as well. You can see here we have, different examples. On this image, we're seeing a pile jacket where the anodes are being installed around the circumferential of the pile, and they're connected all together and then connected to the steel here. On this image here, we have an overbuild where all the deteriorated concrete is removed. The galvanic anodes, you can kind of see they're being installed in rows here, and so on and so forth. And really, the big takeaway with distributed anode systems is that they can be used to provide cathodic protection and satisfy cathodic protection performance criteria. Out here in the US, we use the AMP standard, which designates specific criteria that need to be met in order to achieve cathodic protection criteria. For our international audience, they may use the ISO standard. And so, these anodes are able to achieve that, and they're a little different than other forms of galvanic anodes. And if, referring back to George Sergey's presentation, the previous webinar that was done, if you haven't done that, definitely check that out. Fundamentally, these anodes are different than what George presented on, and they are a high capacity anode compared to other galvanic options. Now, obviously, with different applications, there are different types of anodes that can be used with different environments and different settings. So here we have the marine applications, and they're really two different types of anodes. We have the DAS, which is mortar encased. We have the standard and a marine anode. The standard is typically used for in dry land, freshwater or brackish water applications, and sometimes, atmospherically exposed saltwater applications. And the marine anode is also mortar encased with a highly alkaline mortar. And that's typically used in transitional zones or tidal zones of the piles. And then the tidal plus anode, the second type of anode, is again used in saltwater applications in the tidal and transitional zones. And so you can see here, the anodes are installed on the face of the pile. They're connected together, and then either they're directly connected to the steel, or we have specific wires that go into a junction box or a monitoring box, and we're able to assess the performance of the CP system. For overbuild and overlay applications, they have the mortar encased regular alkali activated DAS. And you can kind of see in this image here, we can see the zinc anode core with the grooves on the surface. And that zinc core is encased in a highly alkaline cementitious mortar around it. And here on the left, we can see this was an overlay application where the deteriorated sections of the bridge deck was removed, and the DAS anodes were laid at the specified spacing or at the design spacing to provide cathodic protection. And the image on the right, that's a new construction. So the owner wanted to, get an extension in service life from the get-go, and so the DAS anodes were prefabricated inside specific elements of the structure. And lastly, we have the surface-mounted DAS anodes. Again, these are distributed anode systems. They're the exact same type of anode, but just a different application. They're very useful for structures where we have low concrete cover, where we can't remove a lot of the concrete and install the anode in place. So we can just easily apply it on the surface in pre-stressed concrete elements, and as well with if we have structural elements that are heavily reinforced, and we physically just don't have enough space to put the anode inside the concrete, we can install the anode on the surface. And on this image, you can kind of see we have the zinc core with the grooves encapsulated in that alkaline mortar around it. And there is mortar applied on the surface, so that provides that electrolyte between the anode and the concrete element that's intended to be protected. And then all of that is covered by this PVC casing over here. And so this was a project example that was used for overhead applications. We had very low cover depth here, so we decided to use the surface mounted anodes. Now, going into the design parameters, obviously, as engineers, it's important for us to holistically understand the parameters and be able to identify them before we jump into the design. And these 6 are the ones that I thought of as most critical. Obviously, there would be more, but to me, these are the 6 questions I always ask owners or asset owners before I can conduct a design. The first one, and I'll be going into each of these more in depth, but the first one is environmental and exposure conditions of the structure. Second one is the risk classification. What kind of risks are we dealing with? How much chloride content do we have? What kind of environment, is that in, and how does that affect the risk of our structure? And then understanding the electrolyte information. Obviously, are we dealing with salt water, fresh water, concrete, soils? What kind of electrolyte information do we have there? And then selecting the appropriate design current density. That's probably one of the most critical parts of any design. You have to be able to select the correct one in order for you to be able to overcome that corrosion current. And then lastly, understanding what service life extension or service life requirements is the owner looking for, so that you don't under design or over design. And then lastly, determining how much steel you're ultimately trying to protect. So with that, going into the environmental and exposure conditions, This is a steel sheet pile wall, and we can see that it is severely deteriorated, and there's a lot of corrosion. You can clearly see that one has lost quite a bit of section. The important thing is to note is that, there's an underwater region of that sheet pile, which does have corrosion activity going on, but there are also different other regions that are experiencing corrosion, such as the tidal zone, which is exposed to regular wave action, and then the splash zone, which is atmospheric, but from time to time it can experience wave action as well. And so all of these three different regions are experiencing corrosion at different rates. And so it's important to keep that in mind when you're doing a design, is to design the distributed anode system appropriately so that all those regions are being protected and you're using the right type of anode at the right spacing and the right quantity. And so here's a real life example that I would like to use. This was a bridge structure, and a lot of the piles were exhibiting signs of corrosion damage, and so we were able to obviously divide each of the piles into specific sections and design the distributed anode system accordingly. And so you can see for the underwater sections, we have 3 anodes over here at various different lengths to fit the section of the jacket. And then the tidal zone and the splash zone, obviously the anode quantities increased because they were in different risk categories and exposure conditions. And so just because it's one element, it doesn't mean that one solution would fit all the different exposure conditions, or the environmental factors need to be taken into account. Next is obviously the effect of temperature. We need to understand how does temperature affect corrosion rate, but also our anode current output. And so here is a test a field trial that we did out in Ohio with the distributed anode systems. And on the graph on the left here, on the x-axis, we have the reciprocal of temperature in Kelvin, and on the y-axis, we have the logarithmic values of the current density that was produced by the anodes. And so we can kind of see there's a linear relationship there. And we could see from this result that as the temperature increased every 10 degrees Celsius or 50 degrees Fahrenheit, our current output from the anodes almost doubled. And we compared that to laboratory trials where we were just looking at corrosion activity in general. And again, we have the logarithmic current on the y-axis and reciprocal of the temperature in the x-axis. And again, we were able to see that same linear relationship with temperature and current output. And so I guess the takeaway from this slide is to understand that as your temperature increases, your current, both your corrosion current is increasing, but also you need to design and consider that when you're designing any sort of corrosion protection systems. And so looking at that and understanding the effects of temperature on current output and corrosion current, when we're designing any sort of distributed anode system, we need to determine, okay, what kind of mean exposure temperatures are we dealing with? Where is our structure situated? Is it in Alaska or is it in Florida? Because obviously those have very different mean, those regions have different mean exposure temperatures. So if we're dealing with temperatures that are around 10 degrees Celsius or less, 50 degrees Fahrenheit, we can utilize the standard DAS anode. But if we have temperatures that are greater than that, then we need to utilize the DASX, which is a larger anode. Because we know with higher temperatures, we require more current, and more current, requires more mass to last us that service life, that design service life. And the important thing here is to note that, the internal zinc embedded in both of these anodes, the surface area of it is exactly the same. It's just that the DASX has more mass to it, and you can clearly see. So the DAS is around 0.65 pounds per foot, whereas the DASX is 1.65 pounds per foot. So it's almost triple the amount of mass. And And so we just need to ensure that we have enough mass to last us the desired service life. Next would be the risk classification. Obviously, depending on what kind of chloride content and environment you're dealing with, your risk significantly changes. And I like to divide them into 3 different categories. We have low to moderate, where we have chloride contents that are between 0.2% to 0.8%. Here we know that there is some chloride level, there are some chlorides, but corrosion is likely to occur, but it's at a low to moderate rate. With the high risk classification, our chloride levels obviously increase. We're between 0.8 to 1.5%. We have enough chlorides for significant corrosion activity, especially taking into account if we have higher temperatures, then you're definitely in a high risk category. And then extremely high would typically tend to be where we have significantly high chloride levels, 1.5% or above, with elevated temperatures or marine environments. Typically, we're in that category. We're in that risk category when I'm from Florida, so most of our structures would be classified in that category. The next step is understanding your electrolyte. What kind of electrolyte environment are you dealing with? With that, resistivity is one of the factors that we look at. If you have very low concrete resistivity values, your risk of corrosion is high. And conversely, if you have very high resistivity values, your risk of corrosion is relatively low based on previous research that's been done. And resistivity is a double-edged sword, because if you think about it, if you have no corrosion protection systems installed and you have a very high concrete resistivity, the corrosion current on a microscopic level is limited because of the high resistivity, the corrosion current cannot be spread out wide. And on the opposite hand, if you have low concrete resistivity, the corrosion current can spread pretty wide throughout your structure. And so when you look at it, when you're designing a distributed anode system, you're really using the same theory as a corrosion cell, right? You're installing these distributed anode systems and connecting them to the steel, and they sacrificially corrode to protect the steel element. So if you have high resistivity concrete, you would have to be very careful with your anode spacing and how far apart you place the anodes, because of the current reach from the anodes. And so if you have lower concrete resistivity, and that's why with a lot of anode systems, you can see on the manufacturers, they limit the concrete resistivity to a certain amount, because after that, if you supersede that concrete resistivity values, the anodes won't be able to, the current of the anodes won't be able to go far out. And so that can have an impact on the anode spacing. And the most important one of them all is selecting the appropriate design current density. You have to pick a design current density that is at or higher than what your corrosion current density is. You have to overcome that corrosion current. And so in selecting your design current density, that it's based off of 2 things. One is your risk category, which we discussed earlier, and the other is temperature. So depending on what kind of temperature, mean exposure temperatures you're dealing with and your structure is located at, you would have to pick the appropriate one. So if let's just assume we're in a high risk category, and if we look at, mean exposure temperatures of 50 degrees Fahrenheit or less, we're at a current density of 0.11 milliamps per feet squared. And if our temperatures are elevated, let's say we're located in Florida, you can see that the current density at the end of design life is almost doubled. It's 0.22 milliamps per feet squared. And the big takeaway from this slide is that when we're designing distributed anode systems, we need to look at how much current is the system producing at the end of its design life, because that's very important. We need to ensure that the anodes are able to output enough current at the end of service life, not just at the beginning. And so based on your risk category, how much chloride content levels you're dealing with, and your exposure conditions, as well as temperature, we're able to select the appropriate current density. Service life is obviously another important factor because that can significantly affect the type of anode and also your spacing and your design. The one thing service life doesn't affect is the design current density required at the end of service life and what current density you design with. However, it would affect the type of anode as well as its spacing. And so I'm going to use an example here. Let's assume that a structure is exposed to mean temperatures that are greater than 68 degrees Fahrenheit. We're located somewhere tropical like Florida or the Middle East. Our structure has a steel density of 0.72, so it's moderately reinforced, and our concrete resistivity is around 30 kilo centimeters. So it's a high, relatively high concrete resistivity, and the risk category is high. We're dealing with chloride content levels that are between 0.8 to 1.5%. And so I've done two designs here. Design number one is for a 20-year service life, and design number two is for a 25-year service life. So there's a 5-year difference. And I've done the design for the two different types of anodes. So if we were to use a DAS anode for the 20-year service life, we would be at 19 inches on center. And the DAS-X, which is a larger anode, would be at 26 inches on center. So we're able to, obviously, we know that DAS-X is larger, so we can space them far apart. Now, if we look at the 25-year service life for the DAS anode, the anode spacing is reduced to 14 inches. So it's reduced by 5 inches, and we can see just by increasing our service life by 5 years, our anode spacing has been reduced. And similarly, if we look at the DAS-X, the anode spacing is reduced by 6 inches. So we can see how much of an impact service life will have on anode spacing. And so it's important to really do the proper field study and understand the structure before a service life requirement is selected, because that will have an effect on the anode spacing and the type. Lastly, understanding the steel density, how much steel are we trying to protect is critical. Obviously, the more steel you have, the more anode you're going to need to protect it. And so here we have two graphs. On the left graph is for a DAS anode in a high-risk category, and the graph on the right is a DAS-X anode in a high-risk category. So the categories are exactly the same. And on the x-axis, we have steel density, and on the y-axis, we have spacing in inches. And so you can see we have different curves for each of our service lives, 10 years, 20 years, 30 years, and obviously we can extrapolate between that. If we need a 15-year design service life, then we can use math to calculate what that spacing would need. But typically, we have 10, 20, and 30-year, which are pretty standard. So let's assume that we have a steel density of 1.2. What we would do, we've calculated our steel density, and that's come out to 1.2. We would draw a straight line to a 20-year service life line, because we want to design for a 20-year service life. And once we hit that chart, we would draw another line all the way to the left until we intercept our y-axis. And that gives us a spacing of about 15 inches on center. So in order for us to achieve a 20-year service life with a DAS anode in a high-risk category, we would need to place our anodes approximately 15 inches on center. Now, if we were to do that same calculation for a 30-year service life, you would do the same thing, and you can see our anode spacing would be reduced down to 8 inches. So we're able to achieve a 10-year service life or a 30-year service life extension, but our anode spacing is significantly reduced. It's almost halved. And so let's look at that same example, but for a DAS-X anode. Steel density is 1.2. We're aiming for 20 years, and our anode spacing would be around 24 inches or 25 inches. Now, looking at it for a 30-year service life with a DAS-X, that's about 12 inches on center. So we're able to look at, different anode types and different service life requirements and figure out what is the most cost-effective solution for the owner. And from a constructability point of view, what makes most sense. One thing to note here is that the distributed anode systems are typically limited at 28 inches on center. So their spacing is limited to 28 inches on center. And that's because, based on past projects and studies that have been, laboratory studies that have been done, we know that the current reach for the anodes are about 14 inches on either side. So if we were to place an anode at one location, it would be able to throw current 14 inches to the right and 14 inches to the left. And if we were to exceed that spacing, then there would be an area where your anode is not really able to protect that steel. So it's very, very important to be able to keep that in mind. Going into the marine pile jacket example, I've outlined some of the steps that I typically conduct during my design practices. Step one is really to understand what service life requirement I'm dealing with. How much am I trying to extend the service life of the structure by? And these are very important questions that we could ask the owners or the engineers that we're working for at the beginning of the project to be able to provide a viable solution and an appropriate solution. Step two is really calculating our steel density to see how much steel we're trying to protect and how much steel we're dealing with. For column structures or piles, usually steel density is calculated per linear feet of that element. And then step three is determining the risk category, figuring out how much chloride content are we dealing with at the reinforcement depth, because as you saw, that significantly affects our risk category and the design current requirement for it. And so it's always good to go out to the structure and collect powder samples or core samples and send those to the lab to get analyzed, to have an idea of, a real idea of how much chloride content is that structure exposed to. And we can collect that at different, sections of the same element to really narrow down our design. And obviously, if we're not able to do that, then the best step would be to use our engineering judgment for assumptions based on maybe previous projects or previous structures that we have done designs for that are in a similar exposure condition. And then step four is figuring out our mean exposure temperatures. Where is the structure located? Is it somewhere tropical? Is it somewhere, like Alaska or Canada, somewhere that has lower mean exposure temperatures? And then once we've determined the risk category and our mean exposure temperatures, then we're able to determine our current density at end of service life. And then once we've done that, we can do some electrolyte study. In my case, it will be concrete resistivity, figuring out what kind of concrete resistivity we're dealing with, because as we discussed, concrete resistivity can affect the anode spacing. And then with all of that information, then we're able to make a judgment on what anode type, what distributed anode type is the most effective. And the next step would be to essentially calculate its spacing. And so here's a project example where we did some marine pile jacket designs, and in the highlighted orange section, we have all the different pier numbers on the first column. Then the second column are all the pile ID numbers. Each pile was obviously exposed to different water depths, and so the jacket lengths are obviously varying. So we're able to, break that down in our bid documents for the contractor and the owner to really be able to digest it all. Then the green section is the designed anodes, distributed anodes for the submerged section of the piles. We have different varying lengths, 1.5 feet, 3 feet, and 6.5 feet of anode length. And so we're able to tabulate those so that the contractor can easily digest all this information and know exactly what anode length he would need for which pile at which location. And lastly, those are, the highlighted blue section is for the atmospherically exposed portion of the pile. Again, as we discussed earlier, there are different types of anodes that need to be used for atmospherically and submerged portions of the piles. And so all of this is divided per pile. So the contractor can look at pile number 1. We need 16 feet of anode for the submerged portion and 13 feet of anode for the atmospherically exposed, and get the different anode lengths specific to that pile. And in some cases where we're not able to extend the jacket fully up to the mud line, for whatever reason, sometimes the piles are just way too long. Sometimes the submerged portion of the pile is in good condition. We don't really need to have a jacket there, but there is corrosion activity and we still want to protect it. We can definitely use galvanic bulk anodes in that situation. And obviously, depending on the water salinity and some other water factors and water chemistry, we can pick the right type of bulk anode for it. So typically for fresh water, we use magnesium. For brackish water, we use aluminum. And for salt water, it's either aluminum or zinc. Typically, we go with aluminum, but zinc can be used as well. And just going back to that example that I showed earlier in the presentation, here we have the pile, and we can clearly see, as I explained earlier, we have the submerged portion of the pile with different anode types and anode lengths and spacings. And here in the tidal zone, obviously that's prone to more corrosion activity. The anode spacings are tighter. And then once we get to the atmospherically exposed portion of it, again, the anode spacings are even tighter because the risk category in the atmospherically exposed was higher. And so we needed to make sure that we can overcome that corrosion current. And then we have some section views of the pile. So this is section A1, which is right here. We can see the original pile, concrete pile, and the anodes are placed around the circumference of the pile. And they're attached to the pile, and a stay in place form is around them, and concrete is poured in that annular space to fill it. And in this situation, we did have a monitoring box where all the anode wires would go inside this monitoring box with structure wires, and that would allow us to interrogate the system and make sure that we are achieving cathodic protection criteria over the years once the system was commissioned. And so as part of that, having structure connections and ensuring electrical continuity of all the steel elements inside your structure element is vital. The first step is to make sure that all of your steel components that you would like to protect are continuous with one another, electrically continuous with one another. Once electrical continuity is established, then the next step would be to install structure connections. Here we have 3 different options that we typically provide. First one is a pin braze connection. Second one is a drill and tap connection. And the third one is a bolted connection. And so the contractor can use whichever option they would like and they find easier. And they make a structure connection to the steel reinforcement and take the wire up to the monitoring box or junction box. And we're able to terminate the wires inside the junction box and monitor the CP system's performance. And so here's an example of a typical junction box or monitoring box. We can see the red wires are all the anode wires coming in and terminating to one end of the shunt. And our structure wires are coming in and terminating to the other end of the shunt. And this shunt really allows us it has a known resistance. So we're able to measure the current output of the anodes and see how much current the anodes are producing. And this connection over here, that's a structure connection where we can use it to measure the corrosion potential of the jacket and see what kind of corrosion potentials we're dealing with before and after the commissioning of the system to ensure that cathodic protection criteria is successfully met. Moving on to galvanic encasements, the design procedure is the same. It doesn't really change. We still have the same 8 steps. I guess the The only difference between this and pile designs would be that when we're calculating our steel density for slab or wall structure elements, we tend to calculate it in per square foot of concrete area. Again, we would still have to identify our service life, our risk category, our exposure temperatures, mean exposure temperatures, our current density, and then selecting the appropriate anode type and anode spacing. And so here we have an example where an overbuild was done on an abutment wall. So you can see there was an existing bridge deck and an approach slab, and there was a joint, and that joint had failed, and so there was significant water runoff, and it was contaminated with de-icing salts, and as that water ran down, it created a lot of deteriorated concrete because of the corrosion of the steel reinforcement. And so as part of the rehabilitation effort, the deteriorated concrete were to be removed, anchors were to be installed with a new layer of reinforcement, and then these distributed anodes were installed at a set spacing to be able to protect all the steel elements inside that abutment wall. And so here we can see the existing conditions before any repair work was done. We can see the abutment wall has a lot of efflorescences, a lot of cracking and spalling. And so all of that deteriorated concrete was removed. As you can see in this picture, the new mat of reinforcement was installed and the anodes were placed in place. And wires were ran up to a monitoring box from the anode and the structure to be able to monitor the performance of it. And so here's an example of when the forms were installed, the concrete was poured, and we have the junction box or monitoring box right here, which allows us to go back and verify the performance of the system. And then this is what the final product looked like. You can't really even tell that there was any there are any anodes in there. And the last example is, again, an abutment wall where there was severe deterioration going on. And so you can see the hydro demo removing all of that deteriorated concrete and exposing the embedded steel. And once that was done, the distributed anode systems were installed, and you can clearly see they're being directly shorted to the steel in this case. So there was no monitoring. The distributed anode systems were just connected directly to the steel, and the construction crew is kind of hanging them right now. And here's an elevation view that you can kind of see all the anodes being installed at a set spacing. And yeah, so with that, I open the floor to any questions.
All right, thanks for that, Shayan. Yeah, this is now we're getting to the Q&A. So if you do have any questions, please do get those into the Q&A function there. I'll start sending them through here, and we'll get them passed on to Shayan to answer. So Mason asks, in a 35°C environment, would you be tripling the current output requirement for an anode system?
It would. That's a good question, and so determining the exact ratio of how much the current would increase by would, again, obviously we know that it's a linear relationship, but there are other factors that play into that. So it would depend on the concrete's resistivity, how much chloride exposure, and what kind of risk category you're in. If you're in a high risk category, you may need to increase it even more. If you're in a low category but higher temperatures, it might not be required to be increased as much. So you would have to look at that specific structure and its risk category as well.
Sorry, I was muted there. Sorry. I just had a good one here. So are you able to reinstall another cathodic protection system in the future, or to like past 50 years, or how long Sorry, if you
Yeah.
wanted to say reach like a 50-year design life.
Yeah, so there are multiple different routes that you can take to achieve a 50-year service life extension. Again, that would depend on the structure. However, we've had projects in the past where it's just a blanket statement. It's very hard to achieve a 50-year service life extension just purely on galvanic CP systems. Typically, we would, if it's viable, we would switch to an impressed current cathodic protection system, because those anodes are a lot more noble, and we use an external power source to provide the current and the electrons, so they tend to last longer with proper maintenance. But we've had projects in the past where we've designed 2 galvanic systems, each for a 25-year service life. And so what we did was we connected the first set of system immediately during the first phase to last us that initial 25-year service life. And then the second system would be activated, at 25 years to give us that additional 25-year to achieve a 50-year service life extension. But again, that would very much depend on the structure, the accessibility. What kind of structure is it? Is it in a marine environment? Is it in is it a bridge structure? Do we have proper maintenance teams that can accommodate that? And really plan. It depends on the owner's goals and objectives. So it would really be a joint effort, but it has been done in the past.
So Anonymous asked, how can atmospheric exposure protection work with DAS anodes on steel sheeting? They're wondering, you need like some kind of electrolyte to surround that steel.
That's a very good question. So in that situation, if when we use distributed anode systems on sheet pile walls, it would essentially be encased in concrete. So there would be a jacket, that atmospheric portion would be jacketed, and concrete would be poured in that area. So it would act as the electrolyte.
And Luke T asks, how often do you specify the terminal boxes versus just directly burying the connection in the concrete?
Usually we almost always specify monitoring boxes, just to be able to assess the performance of the system. I can tell you from experience that DOTs and on government projects, they almost always require that. Private owners sometimes, for budget purposes, they're not able to do that, but in the grand scheme of things, adding that monitoring box does not increase the cost of the project significantly. And so it's very useful to be able to obtain that data and assess the performance of the CP system. And obviously the assessment needs to be done by a certified, AMP or ISO certified individual in the corrosion field. But it's important to be able to understand how the corrosion activity is reduced over time. So I always specify it in my projects.
And those monitoring boxes don't necessarily have to be on the entire system, right? You can be on just sample portions of your install.
That's correct. Let's say if you have 100 piles and you don't want to monitor every single pile, and you could select 30 or 40% of the piles to have those monitoring boxes, and just have a statistical analysis of, okay, if all 40 of these piles are satisfying the cathodic protection criteria, then the chances of the rest of the piles achieving that is significant. So yeah, you don't necessarily have to monitor every individual pile.
And Jeremy is asking, is there like data or white papers or research studies that are available for people to verify where we're getting our information and what data we have to back up what we're saying?
Yes, yeah. I mean, you have my contact information. Shoot me an email. I'll be happy to share that information with you. There are a number of AMP published white papers on this system from projects going back 25, 30 years that show the results, and I would be happy to share that with you.
Would you also recommend this type of technology in, say, like a new construction project?
Yeah, we've had owners where, I mean, Florida DOT is the forefront of that, but also we've had projects out in the West Coast of the United States where owners knew that, you know, their structure was going to be in an aggressive marine environment, and they decided to pre-install these distributed anode systems in specific elements of their structure where they knew corrosion was going to happen, and it was going to happen at a high rate. And so they decided to pre-install the distributed anode systems in some of their elements to prohibit the corrosion activity, but it definitely has been done.
And can you monitor performance between the different zones on a pile, for example, in your different exposure zones?
So it's a bit difficult because you would have to have different electrical circuits for each of those zones. And it's difficult because you're establishing electrical continuity for all of the steel. So somehow you would have to split the steel into different sections, and you're not really able to do that. So that's a bit difficult to achieve.
Zamil asks, should it be considered an increase in spacing of anodes or a decrease in spacing with the increase of the resistivity of the concrete? And can the resistivity affect both the corrosion current and the protection current?
Okay, so there are two parts to that question. So if your concrete resistivity is increasing, so if you have a high resistivity concrete, your anode spacing would be reduced. And the reason for that is because the anodes are not able to, the current of the anodes are not able to reach far distances. And so you would need to place the anodes tighter together. But at the same time, that higher resistivity value can help you because even though the anodes currents are not able to reach further distances, the corrosion current is also not able to reach specific distances. So you have to really study the structure and the chemistry of that concrete to understand how far apart you need to space those anodes. And what was the second part of that question, Ben?
Oh, sorry, I just published it up. That one again. So they asked increase in spacing for the anodes, and then they, yeah, I guess you kind of answered it. As the resistivity affect both the corrosion current and the protection current?
Yes. So if you have a high resistivity concrete without any cathodic protection current, obviously there is corrosion activity happening, but it's happening at a slower rate, I would say, but there is still corrosion activity. And then obviously that, if you do install a CP system with distributed anode systems, it would obviously affect the corrosion current output of the anodes as well.
Okay. Anonymous asks, are the spacings you indicated expected to achieve the full 100 millivolt depolarization or some fraction of that based on contamination?
Well, when you're designing the CP system, you would definitely want the system to achieve at least a minimum of 100 millivolt polarization shift. And I think that Anonymous is referring to either the AMP or ISO criteria for cathodic protection systems. And so when we're designing any sort of cathodic protection system, we keep that in mind, and the spacings that we design for are designed to achieve that criteria.
All right, we're getting a lot of good questions here.
Yeah.
So I guess Anonymous asks, do you use the mean water temperature or the mean air temperature when you're calculating your exposure condition or your design criteria?
Air. So yeah, you're using your general air temperature, your mean exposure temperatures.
Another anonymous here. So please do get your names included in your questions here. That'll help us reach out to you after the presentation to answer your question. And then that'll also allow us to consider you for the gift card. Anonymous asks, is there an upper limit on the chloride concentrations for these systems?
I mean, not really. I mean, the higher the chloride content, the higher your risk category goes. And, if it is above the 1.5% by weight of cement that I indicated in my presentation, then, the calculations need to be a little bit more rigorous, and you would need to take that into account when you're designing your system. But we've had projects that the chloride levels were significantly higher than that 1.5%.
And with a monitored system, do you install a permanent reference cell or a coupon?
Typically so it depends. For marine structures, typically we use a submersible reference electrode, so a portable reference electrode. We typically don't install permanent reference electrodes because they tend to go bad in aggressive environments. With overlays and overbuilds, we do install permanent reference electrodes in the concrete.
All right, here's I think a tough one for me anyways. Do you factor in like new epoxy coated rebar in your steel density calculation when you're designing or getting your steel density for a overbuild?
Yes, so that's a very good question. So in that example that I showed with the abutment overbuild, you could see that the rebar was epoxy coated. And so when we're calculating our steel density, obviously there are going to be imperfections in the epoxy coating. And if the way we go about calculating that steel density is we would calculate the steel density as if it was regular steel and then apply a factor to it for the imperfections. So we would, that would obviously significantly reduce your steel density because it is epoxy coated, but there are imperfections in the coatings. And so we would apply a coating degradation factor in the calculations so that the epoxy coating rebar is also included in the steel density and is being protected by the galvanic distributed anodes. Good question.
Anonymous asks, I guess for a tunnel wall with a thickness of 1.1 meters, that's a thick wall. How can we protect the back layer of reinforcement?
Well, there are different ways you can go about that. You could either drill holes and install the DASs vertically so that you could protect both layers, but we would have to look at that project a little more in depth because we want to ensure that both mats of reinforcement are electrically continuous with one another. Because if they're not continuous, then there's really, you would have to make openings and establish electrical continuity between the two mats. But feel free to reach out to me. We've had projects in the past with that situation, and we've provided some options, and I'll be happy to discuss that with you.
And I think that is a perfect transition because we are out of time for questions. If you did get your question, if you didn't get your question answered, or if you think of some more after the show, we've got Shayan's information here on screen. He's more than happy to talk about his expertise and the things that he's always studying and working and helping our team's research on. And today's recording and slide, like I said at the beginning, will be available soon on our website at wesavestructures.com, same place that you registered for today's event. So the recording will be uploaded to YouTube. You'll find the link there and the presentation, and we'll have links to both of those in that email. And that's it. Thank you, Shayan, for this excellent presentation.
Thank you, everybody, for tuning in today. I hope the information was helpful, and feel free to reach out to me if you have any questions. Thank you for your time.
Thank you, Shayan. And remember, we've got another one of these next month on two-stage cathodic protection, so be sure to register for that one. And thank you all for coming. Let's get out there and save some structures.